This is a joint webinar between Comsof and Hotmaps, in which we will demonstrate how both tools can be combined to plan and design district heating networks. As you know, in the design methodology of Comsof Heat, we need a number of inputs. Beside of GIS data, the technical design parameter, and the material cost, the heat demand data is required. This is very important input since that determines the pipe sizing of the network, and that is a main cost driver for your deployment costs. Now, getting heat demand data for your district is usually a challenge. Utilities can't share the energy consumption data because of reasons of privacy and more specific, the GDPR regulations. But now with Hotmaps, we will show you there is a reliable source of data to estimate the heat demand for buildings. So in this webinar, we will explain you how to extract data from Hotmaps and how to use this to size district heating networks with Comsof Heat. So on this slide, I explain the principle in short. So on the Hotmaps portal, we can extract the specific area under consideration and extract from there the heat density data and the gross floor area. This information can be cross-linked with the building information that we have in our tool, Comsof Heat, and we can map the heat density data on top of the buildings layer to get an estimate of the heat demand per building. So I am Kurt Marlijn, and the next speaker will be Mostafa Falanejad from the University of Wien. He will give you an introduction to the Hotmaps project first. Next, you will hear Joseph Maria Jebamalai, who's working here at Comsof as innovation engineer, and he will explain the methodology to extract the data from Hotmaps. So this is a technical webinar. It will take about 45 minutes. If you have questions, you can ask them in the chat, and we will treat them at the end. So now I hand over the presentation to Mostafa.
Thank you very much, Kurt, for this introduction. If you make me presenter, then I can share my screen. Yeah, thanks. Do you see my screen?
Yes.
Perfect. Thanks everyone for joining this webinar. Today I'm going to shortly speak about the Hotmaps project, but then very fast directly go through the procedure for obtaining and calculating the open source data for heated gross floor area and heat demand density on hectare level for EU28, which was one of the outputs of the Hotmaps project. Hotmaps develops, demonstrates, and disseminates a toolbox to support public authorities, energy agencies, and planners in strategic heating and cooling planning at local, regional, and national level, and in line with EU policies. So what we did in the scope of the Hotmaps project was to develop a toolbox which is user-driven, meaning that we had like 7 pilot areas on board, and their needs were reflected to the development of the toolbox. The toolbox is totally open source, the code, but also the data sets. And what we have developed here is EU28 compatible. We provide data and calculation modules which can be applied to the whole EU28 countries. So the toolbox provides GIS data for heating and cooling sector. Also, some calculation modules are provided that you can apply on these data sets to manipulate the existing data and extract new indicators. And also you can elaborate heating and cooling strategies using the toolbox. The project duration was 4 years. It will end soon in September 2020. And the last but not least, the final toolbox release would be in August 2020. So I don't speak much about the toolbox, just this is how you if you open the toolbox, you will see the front end of the toolbox where you can find the data sets on the left-hand side, and also the indicators will appear on the right-hand side, and you can select different regions. Much more on these and much more information on the Hotmaps project can be found in the project website or the wiki, and also all the data sets and calculation modules can be found in these links. Let's jump directly into the calculation of heated gross floor area and heat demand density for EU28. I start with heated gross floor area density map. You know that the data is scarce in this topic. We don't have much data on heated gross floor area. What we did was, first of all, to extract all existing information, especially from OpenStreetMap. On the first picture, you see that we have listed the 18,000 municipalities, which we will find information on the number of floors from OpenStreetMap. So all in all, it's around 115,000 municipalities in the region that we cover in EU28, and 18,000 of them have information on a number of floors, not completely. It's a different number of entries available in these data sets. What we did then was to randomly extract 150 municipalities, which are quite representative. They are dispersed across Europe, and they are the ones that have the most complete information on the OpenStreetMap. And we try to see how is the behavior between building footprint and the number of floors in those 150 municipalities. The idea was that to generate a function which can be applied for any regions, of course, roughly, and to find out how many floor different buildings have depending on their footprint, because the data on building footprint are more available compared to the number of floors or floor area. And we come up with these functions that tells us, okay, depending on the footprint that the building has, how many number of floors should be approximately in different regions. This was one of the things that we did for getting the floor area and also the surface to floor ratio to calculate how much is that. The other point was heat density map. This was more complex compared to the floor areas, and we also use different layers that has been also generated within the scope of Hotmaps project. They are available, but are not topic of today's webinar. Therefore, I don't talk about them. But shortly on the methodology, how it has been extracted. First of all, our plan was to generate a heat density map which has 1 hectare resolution for the whole EU28. We started from national statistical data, and we gathered a lot of information on the building stock characteristics, population, energy consumption, energy balances, and so on. This information was fed into our building stock model InvertE-Lab, and we then extract information on heat demand on a NUTS 3 level for EU28. This was still far from our goal, which was having heat demand density and 1 hectare level. So we needed to do additional work on the data which we had on NUTS 3 level. There were a set of data sets available from economic activities to data on population. So we had data from JRC, from census on population. We had data on European settlement map showing the buildings across Europe with a very high resolution, 10 by 10 meter, but also some other economic indicators which were available from different institutions like current land cover. And on top of that, we had some additional specific calculation. For example, we used the data of gross floor area, or let's say surface to volume ratio, or other specific data which were calculated and added to the existing data sets in order to obtain heated areas on a hectare level. So this procedure was very intensive in terms of looking into very different data sets and find out how much could be the heat demand in every hectare. The reason for looking in so many different data sets was that all of data sets have their own strengths and weaknesses. Here I have shown like two examples, one regarding the population data sets from JRC, which is on 250 by 250 meter. Then we have a European settlement map showing the buildings where they are located. And we see that there are regions that there is no building, but some population are assigned to those buildings. So this was a weakness, let's say, but on the other hand, we had the possibility to have the distribution of the population in the areas with buildings. So we tried to combine different data sets to get a better estimation for population. Or another example regarding the OpenStreetMap and again European settlement map was the case of Vienna and Athens. You see that the OpenStreetMap covers the area in Vienna very well, so it provides a very good data set for Vienna, but it only covers half of the city of Athens. So that made us to use as much data and information as possible to make sure that we provide a good estimation for the data that we create. Some discussion on the results. Of course, after having those results, the idea was to validate those results. We did it manually for different areas, but also we had pilot areas on boards in the project. So we received information from our pilot areas. In this specific case, I have examples of Frankfurt, San Sebastian, and Bistrița. And we tried to compare gross floor area density map that we have on our top-down approach compared with data coming from those cities in a bottom-up approach. In these graphics, the left one is for gross floor area, the right one is for heat density. What we did was to normalize the data sets to one in order to be able to compare them and then look into the band or let's say the area that these gross floor area or heat densities are changing in different data sets. Comparing these two approaches, top-down and bottom-up, we see that our approach, our top-down approach, and the data sets that is provided on Hotmaps has rather smaller bandwidth compared to the bottom-up approach. This behavior is seen also for the heat demand density, but basically this is kind of a systematic behavior of top-down and bottom-up approach, and this can be seen in other works and datasets that are generated based on these two methodologies. And the differences can be seen more in detail in this graphic. What we did here was, first of all, to scale the heat demand of each single pixel or dot in these maps to the total demand of area. So we have all three case studies, Bistrica, San Sebastian, and Frankfurt. And also we looked into the gross flow area and also heat demand density in those two from and compared the bottom-up and top-down approach. So here the blue color shows that the top-down attributes of heat demand or gross flow area was lower, has a lower share compared to the bottom-up values, lower share of the whole demand, let's say. And when we compare them, we see that, okay, in some cases, like in Frankfurt, in the city center, there are a lot of high-rise buildings, which leads to higher values in a bottom-up approach than our generic approach. And the other behavior can be seen in the other cities, which are smaller cities, and the heat demand are more dispersed. But the differences are not that big. They are in a plausible range based on what we received from our the feedback that we received from our pilot cities. And one very important additional point that should be considered is that the data from municipalities have also considerable uncertainties. So they also don't have really data that shows us how much is heat demand density in certain area, or how much is the gross flow area in certain area. We had to also manipulate the raw data provided by them in order to extract such information in bottom-up approach. So we can conclude that the range provided by a top-down approach was in an acceptable range. This is, however, does not mean that we should not consider the limitations in these two data sets, although it was plausible, but we should note that both heat density map and gross flow area density map, they use statistical approaches. So they don't really consider very local conditions or situations. They are based on generic approaches. And also, we did manual checks, of course, but we didn't cover every single pixel or city across the Europe. We did check cities across Europe, but not everywhere. The other point that should be considered is that some of the input data that we were using were old, like population data, which are from 2010, 2011 census. Then we should consider that heated area per inhabitant often decrease by increasing population density, but we didn't include this into our approach. And we should note that in regions with a strong urban versus rural area gradient, there might be overestimation of heated in residential gross flow areas. And also, we noticed that in terms of non-residential buildings, we have much more uncertainties when it comes to the suburban areas. I think these are the main limitations that should be considered while using these data sets. But rather than that, we can say that the data set provides quite good estimation and a good starting point, especially for the areas that have no data available. It could be very helpful. Yeah, that was it from my side. Thank you very much. I would be happy to answer your question at the end of the webinar. So I hand over back to Kurt or Joseph for continuing.
Thank you, Mustafa, for this explanation. Indeed, when people have questions, you can post them in the chat, and we will treat them at the end. So now I hand it over to Joseph. Come here.
Okay, so until now we saw what is Hotmaps and how do they derive their data sets. Now we are going to see how can we export this data from Hotmaps and how can we convert it to peak heat demand so that it can be easily used in Comsof Heat. So first, let's start with how to access this Hotmaps tool. So the Hotmaps tools can be accessed in following two websites, and you can go to the area you want. So in the top left, you can search for the area you want. So the area of interest in the map. So you can go to your desired area, and then in the right, you can see different options, which are nuts 0, nuts 1, nuts 2, nuts 3. So these are the different level of details. So then if you select nuts 0, it's in the country level. Then once you go to nuts 1, it's into state level. And then nuts 2, it even more divided into different small parts of these regions. And once you go to LEA2 level, you get every municipality level data. And if you want to select your own data, so you select hectare option. So if you want to select the data for the selected area. So you can click the selection tool in the top and select the shape you want to select your desired area. So you can select your desired area here in the map. So once you selected which area you want to download the data, then you can go to the data download. So here we need two different data. So one is heat demand density and the second one is gross floor area density. So heat demand density. So what is heat demand density? So heat demand density is nothing but the heat consumption per year per hectare. So as Mustafa talked about, they have data per hectare level. So we can download data of heat demand density in per hectare level. So in order to download that heat demand density data, so just have to click the layers on the top and then select the heat density total. So once you selected the heat density total, you can see different options. So you can click download layer selection button. So once you click the download layer selection button, the heat demand density data will be downloaded as raster file with .tiff extension. So this is for heat demand density data. And then we come to the gross floor area density. So the gross floor area density is expressed in meter squared per hectare. So which is heated area per hectare. For every hectare, we have heated area, which is gross floor area density. So we can download this data as before. So we can select the gross floor area total, and then we click the download layer selection button. So once we click the download layer selection button, the data will be downloaded as raster file with .tiff extension. So now we have two different files with heat demand density and gross floor area density. So now we can open the QGIS project, and then we can open this heat demand density file in the QGIS project. And you can see I opened the Glasgow HTD, which is a heat demand density file. You can see the higher and lower value here. So you can also drag the file to put it in QGIS. So now it's a raster file, but then we have to convert this raster file to vector file to shape file. So if we have as a shape file, we can use it to calculate heat demand, and we can use it easily with Comsof Heat. So first, in order to do that, so just have to select the layer, so which is heat demand density data file. So here it's Glasgow HTD shape file. So and then go to the raster menu and then click conversion and then click polygonize raster to vector. So if you click the polygonize raster to vector, you will get this pop-up window. So in that you see three different input fields. So the first one is input layer. So which layer we want to convert. So which is of course Glasgow HTD, and then the name of the field to create. So what is the name of the field we want to create? So I put it as HTD for heat demand density data. So you can, after giving the name of the field to create, you can just click run. So once you click run, your vectorized file will be created in QGIS. You can see here the vectorized file is created. Once you have the vectorized file, you can export this as save file. So in order to do that, so you just have to select the vectorized file and then click save future as. Then this pop-up window will be opened. So you can see here the format, file name, and CRS. So these are the three different inputs. So first format, you have to select Esri shapefile and then give a file name and a correct CRS. So once you click OK, then now the shapefile is now created with the heat demand density data, which is in megawatt hour per hectare per year. So now you have the shapefile which contains HDD as a field, and you have all the data per hectare. So this data can be visualized in QGIS. So you can just apply color based on the heat demand density value, and you can overlay the OpenStreetMap to see which are the areas you are looking into. And then once you have this heat demand density file, now we can import gross floor area density shapefile creation. So we just have to repeat the same process for gross floor area density. So now using the same process, the shapefile will be created with the gross floor area density, which is also in meter squared per hectare. So you can see which are all the areas you have higher gross floor area. So the dark red, we have higher gross floor area density, and you have in the white, you see the lower gross floor area density. So once you have these two different files, so now you have two shape files, one with gross floor area density and one with heat demand density. So now we have to map this data into buildings layer. So in Comsof Heat, the starting point is we need to have the buildings shape file, so that we can download it from OpenStreetMap. So we need to map these two different shape files to on the building base layer. Now we have a building base layer, and then we need to map these data. So first let's map the heat demand density data to the buildings layer. So in order to do that, we want to open two shape files, which is the building shapefile and then heat demand density shapefile in QGIS. So here in this window, I opened two different files. So once you have two different files, so you can go to vector menu and then click data management tools and then join attributes by location. Once you click the join attributes by location, a pop-up window will be opened, and you can see here the input layer, join layer, geometric predicate, and join type. So these are four different inputs we have to give it. So what is this input layer? So the input layer is the base layer with which you want to join the data from. So the input layer is buildings file. So you have to select the building shapefile as input layer, and then join layer is heat demand density file. So it will take the heat demand data from the heat demand shapefile and put it in the buildings shapefile. So we get attribute of heat demand density in the buildings shapefile. So then the third one is geometric predicate. So what it means is we need to map the data from the heat demand density shapefile to the building shapefile. So we need to map these buildings to this hectare level area. We need to map this. So we can do it in, for example, using intersection or contains. So we need to map these two data, match spatially to take the heat demand value to put it in a building. So once you select the geometric predicate intersects and contains, and then we have to select the join type. So how to join these attributes? So we have to take attributes of the first located feature only. So you have to select the option which is take attributes of the first located feature only, which is 1 to 1. So the reason is, so one building can be matched with two different hectare squares. So in that case, it will take the first located feature. So because we need one value for heat demand density, one value for gross floor area density in the building level. So we select this join type and then we click run. So once we click run, so we will have the joint layer which is created as a shapefile. So now we have the joint layer with heat demand density data which will be created, and then we can export that file as shapefile. So once you export that shapefile, you can see you have the buildings shapefile with all the attributes from the building shapefile, and also the HDD attribute we just created, which is heat demand density. So you now have all the heat demand density values in each of the buildings. So then once we have this data, we can visualize buildings with different heat demand density values. So these buildings can be visualized with mapped heat demand density. So you can see here these buildings with dark red, you can see you have a higher heat demand densities, and you have with the white colored buildings which have lower heat demand density. So you can easily visualize which are all the building have high potential to connect to the district heating systems. So then now we have to map this gross floor area density to the joint layer. Now we just map the heat demand density value to the building shape file. Now we take the joint layer and then we map that with gross floor area density. So in order to do that, we just have to repeat the same process. So now the base layer is going to be the joint layer, and the gross floor area density is going to be the joint layer. So first we open the joint shapefile and gross floor area density shapefile in QGIS. Then as before, we go to vector menu, data management tools, and joint attributes by location. So now the input layer is going to be joint shapefile, and then the joint layer is going to be gross floor area density shapefile. And then we select the same geometric predicate as intersects and connects, and joint type we select the same, take attributes of the first located future only 1 to 1. Then we click run. Then now we have a layer of building shapefile with the heat demand density value and also the gross floor area density value for each building. Now we exported these two values in our building shapefile. Now we can see how to calculate or how to estimate the heat demand based on this data. So heat demand estimation. So two inputs we exported from Hotmaps. So one is heat demand density and the second one is gross floor area density. So as I said, heat demand density is in megawatt hour per hectare per year. So it's heat consumption per hectare per year, and also gross floor area density, which is heated gross floor area, which is in meter squared per hectare. So for the calculation part, we first have to calculate heat demand density per square meter of gross floor area, which is in kilowatt hour per meter squared per year. So in order to do that, we just take this heat demand density value, multiply by 1000 to get it in kilowatt hour per hectare per year, and divide this heat demand density by the gross floor area density, which is in meter squared per hectare. So now we get kilowatt hour per meter squared per year. So this is the value of heat consumption per meter squared of gross floor area per year. So now we have these values, which is kilowatt hour per meter squared per year for every building. Now we just need heated building area for each building. Once we know the heated gross floor area of each building, we just have to multiply that value with this particular kilowatt hour per meter squared per year. Then we will get kilowatt hour, which is heat consumption per year. So if you already have your data for heated gross floor area, you can directly use it. If we don't have that data as well, then we can approximately estimate the building gross floor area. So the building gross floor area can be estimated using building footprint, which is from OpenStreetMaps. We can calculate the building footprint, and then we can apply a scaling factor. So why do we have to apply a scaling factor? Because the building footprint we obtained from OpenStreetMaps, which also contains gardens or other spaces, which not necessarily needs to be heated, and also it does not take into account for different floors. So we need to have a scaling factor to take this account to change this building footprint to the heated building gross floor area. So first, how do we calculate this scaling factor? So Hotmaps already does approximations, and they already calculated the total heated gross floor area, so which we take from Hotmaps, and then we can calculate the total building footprint from OpenStreetMaps, and then we just divide these two values to get a scaling factor. So once we have the scaling factor, we can multiply with building footprint to get building gross floor area. Now we have the heated building gross floor area. We can multiply that with the heat demand density per square meter of gross floor area, which is in kilowatt hour per meter squared per year, to get it into yearly heat consumption. So we can calculate yearly heat consumption with these two values. So now let's see how we can calculate building footprint, which is area of building polygon from OpenStreetMaps. So we have a building footprint which can be calculated. So we can open field calculator in QGIS, and we can create a new field and put a output field name. In this case, I put build FP for building footprint, and then we just have to put $area in the expression, and then if we just click OK, then we have this building footprint area for each of the building. Now we have the building footprint for each buildings. Then now we have to calculate the scaling factor, as I said before. So the scaling factor is going to be total gross floor area from Hotmaps divided by total building footprint from OpenStreetMaps. So you can see this is the Hotmap interface. So in the layers, if you click heat demand, heat density total and gross floor area total, in the right side you can see the results. So here you have a gross floor area which is approximately 1.6 million meters squared. So we can just use this data, we can put it for total gross floor area from Hotmaps, and we already know the building footprint for each of the buildings. So we just have to sum all of the building footprint to get the total building footprint from Hotmaps. Now we have the scaling factor. So once we have the scaling factor and the building footprint, we can calculate approximate building gross floor area. So once we have calculated the building gross floor area by multiplying these two values, then now we can calculate yearly consumption by multiplying building gross floor area and heat demand density. So here in this screenshot you see the building footprint, which is building FE for each of the building, and you have scaling factor for each of the building. So we just multiply these for every building to get gross floor area for each of the building, and we use this gross floor area for each building, and we also calculated kilowatt hour per meter square for each building. We just multiply these two to get heat consumption per year. Now we have heat consumption value which is in kilowatt hour per year for each building. So now we can have an option how we can calculate peak heat demand from the yearly consumption. Now we have yearly consumption for each building. So we have two options. So the option one to calculate peak heat demand from the yearly consumption is using full load hours. So we can calculate peak heat demand by dividing the yearly consumption by full load hours. So which is approximately around 2000 for residential consumers. For other building types, you can have other full load hours depending on the location and the use case. So once you have full load hours, we just divide it with yearly consumption. So we directly get the peak heat demand. So the option two can be using the following formula. So which is the peak heat demand, which is equal to peak monthly consumption divided by time with load factor. So the load factor is associated with different building types. So for each building type, we can have different thermal load factor. For example, for shopping mall, it's 0.36, residential is 0.4, office is 0.47, and hospital is 0.5. And so these values are different for different locations and different projects. So you have to make sure that it's suited for your own location. And then we have the time, which is total number of hours in peak month, which is in January. So it's 744 hours. And then for peak consumption, we can take, for an example, 16% of yearly consumption is we are consuming for the peak month. So using these values, we can get peak heat demand for each building. So now here with the heat consumption, we can, with full load hours, we can calculate the peak heat demand, and also using those formula, we can calculate the peak heat demand. Then in Comsof Heat, you can go through the next network calculations. Now you have heat demand, then you can go on to calculate the different district heating scenarios. So now we estimated using this approximate data. It's approximately. So I also checked with did a case study to validate how much is the difference between the actual gas consumption data and the calculated data exported from Hotmaps. So I took a entire municipality of KORTRUK. So here approximately we have 32,000 buildings. I chose all of them, and the gross floor area from Hotmaps, which is showing 4.6 million meters square. Then if we run the same procedure as before, so the gross floor area for total building footprint, which is estimated from OpenStreetMaps, which is around 7.4 million meters squared, but the gross floor area from Hotmaps, which is it's 4.6 million meters squared. So if we just take a scaling factor of these both, so we get a scaling factor of around 0.63. Using this scaling factor and heat demand density and gross floor area density, so it is estimated that total heat consumption is going to be around 732 gigawatt hour per year. But the actual heat consumption data of this particular municipality is 811. So it is obtained from open data source. So it's around 811 gigawatt hour per year. But the difference in percentage is 10%. So in this case, the difference is 10%. So, but it can vary from 10 to 30%, depends on area by area or project by project. So it depends on the data quality we get. So this is not an exact way of calculating and peak heat demand, but it gives you an overview. If you don't have any data at all, you can use this method to calculate pre-feasibility studies using this approximate heat demand estimation. Thank you. So I will hand over to Good.
Joseph, thank you very much for this presentation. Now we'll see if there are questions. So there are a few questions. Mustafa, are you still online somewhere for you, I see?
Yes.
So one question is, where can I access Hotmaps and how can I extract the data?
Well, there are two ways to download datasets. One way is to go to the repositories of the datasets and download the datasets directly from there. The second way, as Joseph showed, it's easier. You can download the datasets either for your selected area, or you can download the whole dataset directly from the toolbox. I write the address once again into the chat box so that everyone can see it. So you can navigate to the toolbox and download the datasets from there.
Yeah.
I think it should be easy then.
And I believe if people just create user accounts, they can freely access the data, right?
For accessing the data, you don't need a user account, but if you are going to run any calculation on your own data, then you need to create a user account. You can upload your own data sets and perform calculations with your own data sets. So user account is rather for the uploading own data sets, visualizing it, comparing it with the default Hotmap data sets, or running calculation modules for their own data sets.
Okay. Another question here: is there a limitation in the area of the district that I extract? I think it's referring to the size of the area. I mean, is there a limitation in number of square kilometers or number of square hectares that you can extract, or is there no limitation?
Yeah, we set a kind of limitations to avoid any heavy duties on the server, because we should consider that the Hotmap toolbox is on TRL level 7, so it's not a really market-ready toolbox. It was output of one research project. So we put some limitations for downloading or performing queries on the datasets. By the way, you can download the whole dataset at once, but for selection of a certain region, there are some limitations, and the limitation is not that small. I mean, you can still download regions with a size of, I don't know, half of Germany or half of France. So it's still, I think, not very huge limitation or big limitation.
Okay, thank you. And then there is one more for you. Is data available for smaller towns or only for the major European cities?
As I mentioned in the beginning of the presentation, it's EU28 compatible. So the data is available for all areas across Europe, cities, regions, villages, towns. So it's available everywhere.
Okay, thank you very much.
As I mentioned, just one point. As I mentioned in the presentation, the quality of input data was different across different areas. So we may experience some difference in quality of the final values. It should be also be considered, and also it should be considered that it is for pre-feasibility studies. We suggest to use it, especially when you go very in detail calculations.
Okay, well, that's all then. Thank everybody for listening. There will be a recording of this webinar on our YouTube channel latest next week. If you have in the meantime questions about some of the topics, you can send us an email and we'll be happy to answer you. So thank you very much for joining this webinar, and have a nice afternoon.
Thank you, Kurt. Thanks, Joseph. Thanks, everyone. Bye-bye.
Bye.
Bye.